Jacques Laskar introduced to us this morning.
Okay, so hello everybody. So I'm a PhD student at the Paris Observatory with Jacques Laskar and Gonalgue. And so I will explain what we've done for to include the chaos induced by the mean-motion resonance, the first-order mean-motion resonances in the AMD-stability that Jacques presented this morning. So just a recap if you were not there this morning. So the angular momentum deficit is defined as the difference between the angular momentum of a system that is coplanar or circular minus the actual angular momentum of the system. And so this quantity is conserved in the circular system. And therefore, if the AMD is low enough, we have a constraint on the eccentricity of the orbits. And so the collision can be, and we can forbid the collision between the planets. In order to quantify this criterion, we can compare the AMD of the system, the total AMD of the system C, to a critical AMD for each pair of the planets. That depends on the ratio of the mean-major axis and the ratio of masses between the planets. And so this critical AMD is bigger for wide separation, but very small for small separation. However, the AMD is not conserved in the outside if the secular hypothesis is not valid, which is the case in presence of mean-motion resonances. And moreover, a system can be chaotic if several mean-motion resonances are overlapping. So as you can see in both simulation made by DEC in 2013, they compare, so here is the semi-major axis difference, and here is eccentricity for different mass ratios. So here it is 10 to the minus 6, and here it's 10 to the minus 4. Blue means instability because it's a small Lyapunov criterion. And so we see that there is an area where the system becomes unstable before and it's growing with the masses of the planets. So we can estimate the width of the size of this chaotic zone with the application of the Chirikov criterion of the overlapping of the resonances. And so this has been done by several authors, so Wisdom in 1990, and more recently Mostian and Wyatt and DEC. And so we can see here the different criterion that were developed. So the blue criterion is the criterion for circular orbits, and the two lines that you see here are the Mostian and Wyatt criterion and the DEC criterion for eccentric orbits. So those two criterions apply in different cases. So the one that is defined for circular orbits depends only on the mass ratio, the ratio of the mass of the planets to the star mass, and the eccentric orbit depends on the eccentricity of the orbit. And so this criterion was done for like a restricted problem, and the DEX criterion were developed for planetary the planetary problem, free body problem. But you have different criterion for different hypotheses, and it would be better to have something that includes that works for all the cases of orbits. So in order to do so, we redeveloped the Hamiltonian of the mean-motion resonances and try to derive the Chirikov criterion for the overlap of first-order mean-motion resonances. So in order to do so, you have to compute the distance between the two center of resonances and the width of the resonances and compare those two values. So what I give you here is the distance in alpha, so the ratio of the mean-major axis, between the resonance P plus 1 and P plus 1, P plus 2. But we have to compute the width of the resonance. So in order to do so, if the P plus one first order minimal mean motion resonance dynamic can be reduced to a 1 degree of freedom integrable Hamiltonian that is known as the second fundamental model of resonance that was developed by Enrar and Lemaitre, and so I used by several authors, including Deck. So this Hamiltonian has this form, where I0 is the parameter, and X and Y are related to the AMD of the system. Actually, the AMD is split between two quantities, I1 and I2. I1 is the modulus of the X and Y that you see in this plot, and I2 is the conserved part of the AMD. So the width of the resonance in those variables is computed along the x-axis, because this is where the resonance is wider. And the shape of the resonance can be related to the position of the starting mode x3. And that is a very useful remark, because everything can be expressed, all the quantities can be expressed very simply in function of the position of x3. And since we have correspondence between I0 and x3, x3 determines how the Hamiltonian, the shape of the Hamiltonian, of the width of the resonant island. So the width of the resonance expressed as a function of x3 is 4 on the square root of x3. And from this width, we can come back by inverting all the change of variables that were done to go to this Hamiltonian to the width in terms of the physical variable. But so x3 is not a very good parameter to give a criterion that is going to be used for characterizing the overlap of the resonance. And so we introduced another way to determine the shape of the resonance. So we asked ourselves the question of how much AMD a system needs to enter the resonance island. Because since we are looking at the chaotic, we want the resonance to overlap if an orbit is not is circulating inside the inner circulation region. It will not be subject to the chaos induced by this overlap. So we can if the point x equals 0, y equals 0 is inside the resonance, the minimum AMD to enter the resonance is 0. But as I0 becomes bigger, the inner separatrix cross the origin, and we have an expression where the minimal AMD to enter the resonance is the value of the action I1 at the point x2 here, so the crossing of the separatrix with the x-axis. And so we have this expression for the minimal AMD of the resonance, where chi depends on the planet to star ratio, and the mass ratio between the two masses of the two planets. And of P is the order of the resonance. So we have a one-to-one correspondence between I0 and the minimal AMD if the AMD is bigger than 0. And if it is 0, we don't care, because like every orbit will feel the overlap, the chaos induced by the overlap. We can invert the expression that was in the previous slide to have an implicit expression of x3 in function of the minimal AMD of the resonance, and reduce this quantity to something that depends only on the like reduced quantities between the AMD divided by the lambda I, which is roughly proportional to EI for small eccentricities. And we have this curve as an expression of x3 and this quantity. So now how we can use this curve to derive an overlap criterion valid for all eccentricities. So we can come back, as I explained, to the width in terms of semi-major axis, depending on the square roots of x3. And by equalizing the distance between the two centers and this width of resonance, we can have the expression of x3 when the overlap occurs. And we can inject this expression into the previous form, the previous expression of x3 that depends on the square root of small c mine, and obtain this expression that depends on epsilon and p to some power. And using the relation between p and alpha at the resonance, so that alpha is equal to p over p plus 1 to the power 2/3, we obtain the criterion, an implicit expression in alpha and epsilon, but that is where C mine is isolated on one side. So as the previous criterion, at first order it is independent of gamma, so the ratio between the two masses of the planets. We can look at the limit cases of this expression to see if it is consistent with the previous authors. So if we take C mine equal to 0, it corresponds to the circular case, and by solving this equation in 1 minus alpha, we obtain the Dex criterion for the circular orbits. And by assuming that C min is large, which is the hypothesis Dex made to obtain this criterion, we ignore the second term, and again solving this expression gives this value, which is also the criterion proposed by Dex. So we have an expression that is global and that finds the previous results that were proposed for the overlap of mid-motion resonances. So we can plot this. So this is the figure Rex showed you this morning. So we have the first order mid-motion resonances, and you see that the overlap is exactly at the point where the black curve goes through, which is our criterion. And so we have the vertical line is the circular criterion that was in the previous line, and the red line is the eccentric one. And the curve goes from one to the other as C minimum goes to 0. We plotted also the collision line to compare with the previous criterion for the AMD-stability, that was that the planets cannot collide. And we see that this criterion is valid, but only for small separation, and that for bigger separation, the collision is still better than the overlap of first order mid-motion. So how to obtain the criterion of a critical AMD depending on this criterion? So we do exactly the same thing that Jacques showed this morning. We compare the AMD of the system divided by the lambda 2, so the lambda of the outer planet, which has this expression depending on C, instead of the expression with the eccentricity that Jacques saw this morning. And since our criterion that is written here, so G is a criterion, and square root of C mine can be reduced to C1 plus C2 in the maximum case, if we want to maximize it. We have a more simple expression, and so we can derive a critical AMD for the mid-motion resonances. So this is this expression, and so we have to modify this those graphics to those ones. So we have the collision critical AMD, and so for alpha close to 1, we have another curve, and if we zoom, we see that this curve goes under the curve of the collision for values that are close to 1. If we make an expansion in alpha close to 1 in this expression, we find that the critical AMD of the induced by the overlap mid-motion resonance has the same dependence in gamma than the critical AMD developed around this position. And so we have a map in the epsilon alpha plane where the criterion apply. So we have 3 zones. One zone in purple where the collision is still a better indication of instability. One area where this criterion can be this critical AMD can be computed to have a better AMD-stability condition, and this area where every orbit is subject to the overlap of mean-motion resonances, and so we cannot apply the AMD-stability theory because we have no conservation of the AMD and we don't really know what is happening there. So we can wonder what are the effects of this new modified criterion on the AMD classification. So each dot here represents a pair of planets, of real exoplanets from the exoplanet.eu database. And so the color is the AMD-stability coefficient. So here it's just for the AMD, the collision criterion. And so if we add the mean-motion resonance criterion, we see that those systems become less stable. Particularly those one, the beta goes to infinity because the critical AMD is 0. So in conclusion, we present a unified first-order mean-motion resonance overlap criterion, and we can define the AMD stability definition is not changed that much because not many systems are in this region of the phase space. And the new definition of the AMD stability is linked to previous stability criterion that were used that were linked to the Chirikov criterion. And so we plan on working on the evolution of the AMD in this collision region and chaotic region in order to understand what is happening there and how we can enhance the AMD stability theory. And that's all.
Thank you for a nice talk. We are all perfectly on time. So, question?
Yeah. So, if the planets are eccentric, actually the real mean-motion resonance is a 2 degrees of freedom system, and it becomes a 1 degree of freedom system only in the first-order expansion in the eccentricity. So basically, you use this first-order expansion in the eccentricity, whatever is the eccentricity, because that's the only thing can be done.
Yeah, but so the integral Hamiltonian. So for an analytic development, this is what we use because like the literature was using this before. But as you see, like the eccentricities are actually pretty small, where the criterion is better than the collision criterion. Okay. So it doesn't really matter that we use a further development in the eccentricities.
Question? I have one. Could you imagine to use the same AMD stability criterion, but for three body resonances to have an idea if, for instance, a system is more AMD stable or less, depending on exactly on the location of the 3 planets?
So, I think yes, you could develop like an overlap criterion and just use the same framework that we use to derive a critical AMD, but it has the overlap criterion has to be developed for because as you see, the expression is just plugged directly into the critical AMD definition, and so if you just have an expression that you can write on this form, so something that depends on the eccentricity on one side and some constant on the other side, the theory holds for like basically everything as long as you.
But you see this 3-body resonance maybe only in the second order with respect to masses. You regard it only first order resonance.
Yeah, but if you develop the analytical theory to have the criterion, you can have a second order.
Okay. Let's thank the speaker again.